Lee Lind, and I am delighted to introduce Jessika Trancik. Jessika is currently at the Santa Fe Institute and also the Earth Institute at Columbia University. She got her bachelor's degree in material science and engineering from Cornell and her PhD in material science from Oxford. And she is a recipient of a Marshall Scholarship, a Rhodes Scholarship, and a National Science Foundation Graduate Fellowship. And in addition, in between finishing at Oxford and beginning at Columbia, she also worked for the United Nations for a year. So it's a great pleasure to welcome you, Jessika.
Well, thank you, Lee, and thanks for the invitation to be here. Can you all hear me? Okay? No. No? Okay. Let's see. Let's move this guy up.
Follow directions.
Oh, I see. That's what's going on. Yep. Okay. Can you hear me a little bit better now? Yes. Okay, good. Well, thank you, Lee, and thanks for the invitation to be here. I've enjoyed speaking with a number of you over the last couple of days. I'm going to be speaking today about structuring nanoscale materials for low-carbon energy conversion. And in this work, I'm really trying to address the two questions shown here. On the one hand, the big picture question of what is the magnitude of of long-term climate change mitigation? What is the magnitude of that challenge, and what role can nanostructured energy technologies play? So how big is this challenge of dealing with climate change? And then in the second question is, how can we most effectively structure materials at the nanoscale for low-carbon energy conversion devices? So this work is really motivated by the following graph, which shows that atmospheric carbon dioxide concentrations are increasing, as we all know. This is data from the last 1,000 years. And what you can see is on the y-axis here, we have carbon dioxide concentrations in parts per million. And on the x-axis here, you have time. Here you have radiative forcing. You can see that if we look now at carbon dioxide, this curve is going up. It's currently at about 385 parts per million based on the latest measurement in Hawaii. And so that's a problem. The reason is that carbon dioxide traps heat, and this is not new knowledge. In fact, we just recently had the 150th anniversary of John Tyndall's discovery that carbon dioxide traps heat. Okay, so we've known this for quite a while. And the question that I'm going to try to answer for you with a very simple analysis in the next few slides is, what does this mean for engineers? So what is this climate change challenge from an engineering perspective? Okay, so in order to do that, I just performed a very simple analysis trying to get at what our long-term target for carbon intensity for our energy infrastructure is. Okay, so what is the target for all transportation and electricity in terms of amount of carbon emissions per unit energy? So that's what I've shown here, carbon per unit energy. And in order to find that, I looked at a whole range of IPCC scenarios, Intergovernmental Panel on Climate Change scenarios. On the right here, we have emissions scenarios. Okay, so we have year on the x-axis and emissions on the y-axis. So this time we're looking at emissions per year, not concentration, as was shown in the previous graph. And the idea is to say what sorts of emissions trajectories will keep us below a certain carbon dioxide concentration. So in the previous graph, I showed that concentrations are going up to about 380 parts per million. Right, a lot of scientists and policymakers have agreed that we should really stay below approximately a 450 and 550 parts per million concentration in the atmosphere. If we want to do that, then we should pay attention to the scenarios shown in green and yellow. Okay, so these regions here, going from the year 2000 out to 2100, show different scenarios for emissions per year where we can stay below those concentrations. All right, so I looked here at this full range of scenarios going out to 2100. And so that's going to come into the equation here in carbon emissions per year, or CO2 per year. I have C here, but this is really short for CO2. That's what I'm looking at. Okay, and then the other part of the equation is thinking about how much energy the world is going to use. Okay, and so these are different scenarios, again, starting from around where we are today, going out to 2100 for different energy consumption profiles. So you can see, again, there's a huge range here in terms of how much energy the world is expected to consume. Taking 1 over that, we can find this quantity here, which is a target for carbon emissions per unit energy. So that's a sort of engineering target, and that is for all transportation and electricity. And that works out to be these bars here. So on this axis here, I have metric tons of carbon dioxide per unit energy, per gigajoule. And you can see that in 2060, we're about here, 2080 here, and 2100 here. Now, one point I want to make with this is that you hear a lot about uncertainty of climate modeling and scenario building, and that uncertainty is there and it's real. But if you look at the problem from this perspective, you know, given these scenarios, looking at this full range of scenarios, you start to see that this target is really approaching 0. Okay, so there's not a huge range in this target. So that tells you something about you know, how from this perspective, we know with a fair degree of certainty that our energy infrastructure will need to start to approach almost 0 carbon emissions toward the end of the century. Okay, so how does this compare to the technologies that we have today? Here I'm showing, again, carbon intensity, so tons of carbon dioxide per unit energy. And here I'm showing cost, dollars per unit energy, dollars per gigajoule. These are data points from technologies that we have today, and these are average points. So you can see that you have coal that's up here with very high carbon intensity but very low cost. You know, and you have several other technologies along this curve. You can see that you have a range of technologies here with low carbon intensity and getting out to pretty high costs. Okay, so then you can see how this compares to our target. Our average right now is somewhere in between here. So we have some ways to go. And what this also shows you is that there's a kind of trade-off between costs and carbon intensities. These things aren't related totally randomly. You sort of have this trade-off curve here. Okay, now these of course aren't the only metrics that you care about. There are other things you care about. If you want to bring your average down to that target, then you care about the resource size. How scalable are these technologies? And so what I'm pointing out here is that the 3 technologies with the largest resource size, which doesn't mean they're the ones that we should focus on solely. And by the way, I should say that I'm really focusing on electricity here and not transportation. Okay, so a lot of this talk is going to be focused on electricity generation, but you could plot similar curves for transportation. Okay, so the 3 technologies with the largest resource size are coal, nuclear fission, and photovoltaics. I have a question mark here for nuclear fission because there are some questions as to whether we can really extract uranium from seawater, for example, and some questions about whether we would like to use breeder reactors or not. And there are some other issues with nuclear fission, such as waste storage concerns, weapons proliferations concerns, and scalability, as I mentioned, due to uranium and also the use of steel. Okay, but these technologies have fairly large resource sizes, which is important. Okay, now how does this challenge that I've laid out compare to what's happened in the past? So can we put this into a historical context? And that's what I'm showing on the left. Again, this is data that I've gathered from various different sources. And I'm showing 4 technologies: coal, natural gas, wind, and photovoltaics.